Hello everybody and welcome back. This is Chapter 18, Global Climate Change, and this is the third screencast for this chapter. And I'm on the wrong side. I wanted to talk to you about aerosols. You heard me mention aerosols in contributing to chlorofluorocarbons and increasing the greenhouse gases. And I wanted to specifically let you know that aerosols are microscopic droplets and particles, and they, depending on the type of droplet or particle, they can either have a warming or a cooling effect. So for example, soot, which is black carbon, actually causes warming of the atmosphere because it absorbs the solar energy and it can hold that heat. But most tropospheric aerosols actually are coolants because they can reflect the sun's rays. For example, sulfate aerosols that are produced from fossil fuel combustion, they can actually help to slow global warming, at least for a short-term effect, because they can actually reflect the sun. Volcanic eruptions also can cool the earth because the ash prevents the sun from reaching the surface of the earth and warming it, so it remains cooler. So these are some examples of how cooling effects can happen naturally and by the release of fossil fuels. There's another force that we can talk about that changes the energy input, and this is the radiative forcing. And this is the amount of change in thermal energy that a given factor may cause, and there can be different given factors. We can look at these as being positive forcing, which warms the surface, or negative forcing, which cools the surface. So when we look at pre-industrial Earth, and that's at the year 1750, we were pretty balanced in our amount of energy that was entering and leaving our system. But as more people populated the earth and the Industrial Revolution and technology advanced, we experienced radiative forcing of about 1.6 watts per meter squared, more than what our space is able to handle. And this change has been enough to alter the climate. All right, so let's take a look at this graph. So this graph is showing the radiative forcing and expressing the warming and the cooling effect that each factor has on the temperature today. And that's relative to what it was in 1750 when we were looking at watts per meter squared. So when you look at the red bars that you're seeing here, the red bars indicate positive forcing, which means that there's warming that's going on. And the blue bars that you see here indicates the negative forcing, and that means cooling is happening. Now you'll notice that there's something that references surface albedo or cloud albedo. And albedo refers to the reflectivity of the surface. So there is a number of more minor influences that are not necessarily shown, but can also impact that temperature change. So when scientists sum up the effects of all the factors, they find that the Earth is now experiencing an overall radiative forcing of about 1.6 watts per meter squared. This means that today's planet is receiving and retaining 1.6 watts per meter squared more thermal energy than it is emitting into space. This extra amount is equivalent to power able to convert into heat light from 140 incandescent light bulbs. The Earth is estimated naturally to receive about 342 watts per meter squared of energy, and although 1.6 may seem like a small portion of that 342, over time it's actually enough to alter the climate significantly. what this means is that the tropospheric warming that we're going to have will transfer more water into the air, and more water vapor is going to increase that greenhouse gas effect. The effects of increased water vapor, there's some uncertainty to it. They consider two possible feedback loops that could result. A positive feedback loop where we're going to put more water vapor and more warming, which means more evaporation and more water vapor, so that hydrologic cycle will continue. Or a negative feedback loop would be more water vapor, more clouds. The clouds shade and cool the earth, and there would be less evaporation that would happen. So those are two of the possibilities that they see. Because of the feedback loops, minor modifications of the atmosphere can lead to major effects on the climate globally. In the 1920s, a Serbian mathematician, Milutin Milankovic, described three types of periodic changes in the Earth's rotation and orbit around the Sun. He said that over thousands of years, our planet wobbles on its axis, and it varies in the tilt of its axis and experiences a change in the shape of its orbit. And all of this in regular long-term cycles and different lengths. These variations, which we call today the Milankovitch cycles, alter the way solar radiation is distributed over the Earth's surface. By modifying the patterns of the atmospheric heating, these cycles trigger long-term climate variation. This includes period episodes of glaciation, the formation of glaciers during which global surface temperatures drop and ice sheets advance from the poles towards the mid-latitudes, as well as intervening warmer periods known as interglacial periods, where the glaciers wind up melting and we get the global warming. What we see from solar output is that the sun varies in the radiation that it emits. The variation in solar energy has not been great enough to change the Earth's temperature, while there are some scientists believe that solar flares can contribute to this temperature change. When we look at the radiative forces of the solar output, it's only 0.12 watts per meter squared, which is much less than what the human causes. So the impact of the solar output is not as significant. And what we've noticed is solar radiation has actually been decreasing since the 1970s. Okay, so here's that variation in orbit for the Milankovitch cycles that we're seeing. And here's the variation in the tilt or the wobble of the Earth. I had mentioned to you previously that the ocean also is able to hold carbon from the atmosphere. It does hold it in the surface area, mostly within that photic zone, about 200 meters deep. The ocean can hold 50 times more carbon than the atmosphere can because it gets dissolved directly into the ocean water. But what we're noticing is that the oceans are even reaching the total amount of carbon dioxide that they can store, and they're not absorbing as much anymore. What's happening is now when it rains or when the waves or rough seas happen, it releases carbon dioxide into the atmosphere. We're also noticing that since temperatures of the ocean are going up and the waters are warming, that warmer water cannot hold as much carbon dioxide as well. So that impacts the rate of absorption. We consider this as a positive feedback loop because it accelerates the warming of our air. We've mentioned that ocean circulation as well, the ocean conveyor belt. And this is how the ocean exchanges the heat as well, because as the cold water sinks, the warm water rises. This helps to put more moisture up into the atmosphere as winds move over our ocean circulation. We refer to this whole circulation as the thermohaline circulation system. And again, these can affect climates regionally. The northern ocean conveyor belt that comes up the northern United States and the East Coast and then shoots across in front of Greenland and Iceland and goes up into Europe, they believe slowed and stopped in the 18th century and gave a little ice age effect for a while. And they believe that when the melting over the glaciers that form the Great Lakes was what actually slowed this thermohaline circulation and made Europe very, very cold. So what we see with the thermohaline circulation is this is what's going to move the warm tropical water to the north to help to bring that moisture in. We're looking and we're carefully watching Greenland's melting because it has a lot of land ice. There was a big chunk over a mile long, I think it was 1.7 miles long, that just broke off, and there's the concern that its melting could affect and slow the flow of this thermohaline circulation and again put us at the risk of another ice age. We've mentioned the El Nino before, and this is the southern oscillation. And this shifts atmospheric pressure and sea surface temperatures and ocean circulation in the tropical Pacific. And we've seen effects that this can have on creating superstorms like Sandy and other hurricanes. And also it would prevent certain areas from getting enough moisture and causing droughts. So these are all effects that can change the climate. When we look back at our past, we can look at the paleoclimate, and this is the climate of our geological past, and this gives us the baseline to compare to today's climate. One of the things that I said with this is we look at the core samples in order to get an idea of our geological past, and we look for the presence of shells, certain types of calcium shells that can give us an idea of how much carbon dioxide was present. And we know that the more carbon dioxide that's present, the higher the temperatures are. We can consider proxy indicators, and these have indirect evidence that serve as a substitute for direct measurements. Again, proxy indicators can be just like those core samples that can give us an idea of our past climate, and we can look into our rock layers and sediment layers for other information as well. The ice caps and the ice sheets and the glaciers hold clues to Earth's climate history. Carbon dioxide bubbles can be trapped in those ice caps and those ice sheets, which are indicators of climate change. This gives us a great time scale on the atmospheric composition. It tells us more about the greenhouse gas concentrations for those times, temperature trends, snowfall, solar activity, and the frequency of fires, which would contribute to carbon dioxide. The ice core enables us to go back 800,000 years in trying to collect this data and information and understand the global changes that have taken place.